This conference will now be recorded.
Very good morning, students. Today we'll be discussing about the relation between center of radius of curvature and focal length, mirror equations, linear magnification, image formation by spherical mirror, and spherical aberration, its remedy, its uses, etc. So let us see how it goes. So today is the second class on this ray optics part. In the first class, or in the last class, we had discussed about spherical mirrors and its various terminology like pole, focus, principal axis, then aperture, etc. We have already discussed. So today, before we start with our today's topics, let me remind you about the sign convention that we have discussed yesterday. It is very simple. So yesterday, if you remember, I had told you that if we just consider Cartesian, two-dimensional Cartesian coordinate system where the pole is origin and the principal axis is taken as the x-axis and the perpendicular axis drawn through pole can be acting as y-axis, and see any height we measure above this principal axis or along the positive y direction or along the positive y-axis will be taken as positive height. That means, see, this height is actually positive here, but this height, it is in the negative y direction, so it will be taken as negative. Any distance we measure from pole towards right, okay, towards right the pole, okay, right of the pole, that means this is positive x-axis, right? Positive x-axis. So whatever distance we measure along this direction will be positive. Whatever distance we measure in this direction will be negative. Okay? Or the simplest way to take the distances positive and negative measures from the pole is, see any distance obviously will measure from the origin, that is from the pole. So if we measure a distance in the direction of incident light, this is actually incident, this is indent, it is written, so this is incident light, okay, incident light, okay, incident light. Any distance we measure in the direction of incident light is called positive, is taken as positive. Any distance measured against the direction of incident light is actually negative. Okay, that is what it is. Now, see, we had discussed yesterday about the focus. So focus for a concave and for a convex lens. So for a concave lens, sorry, for a concave mirror, the parallel rays after reflection meet at the focus, right? So we can see that this focus is measured in this way, right? In this direction. In case of the concave mirror, the distance PF is measured just opposite to the incident ray, direction of incident ray, or in the negative axis. So this focal length in case of concave mirror, the focal length will be negative. Okay, so this is focal length. Focal length is denoted by small f, so that is always negative. Focal length will be negative in case of concave. Not only focal length, whatever distance we measure in case of concave lens, you can, sorry, concave mirror. Concave mirror, see the CP is the radius of curvature, right? CP is the radius of curvature. So this is also negative here because we are measuring in this direction. You can see that. Okay, just against the direction of incident light. Further, when we'll learn about image formation, there we have three parameters. One is object distance from the pole, then V will be image distance from the pole, image distance, okay, and F will be the focal length that you know. These are actually three fundamental parameters to analyze the image formation in case of mirror or lenses. So this is focal length. So there will be something called mirror equation. They are related in a particular fashion. We will learn that. So all these parameters in case of concave mirror. In case of concave mirror, this will be negative. In case of concave, all these parameters will be negative for concave mirror. But all these parameters will be positive in case of convex. In case of convex mirror, this will be positive. Like see here, the focal length is here, so it is measured along the direction of incident light, so it is actually positive here. Okay, this is positive. See, CP is this one, so this is also positive. R. All right, so all the distances we measured. In fact, yeah, I think only the object distance in case of convex mirror will be negative. Okay, object distance, that obviously depends on where we put the object, but anyway the object distance alone will be negative in case, see, in case of convex mirror, object distance alone will be negative. Otherwise V, that is the image distance, and focal length will be positive. Excuse me. Now we'll go to the next topic, that is the relation between focal length and radius of curvature. So we refer to these two figures. So either of them you can just refer. See, I have taken both. See, this is a concave mirror. So this side is actually polished. In case of this side is polished. Excuse me. This side is polished. So this bulge side will be acting as mirror. This is actually convex mirror, and this is concave mirror. As you see, the concave surface is acting as a mirror. Okay, so see, I have taken a parallel ray. We'll be discussing very soon. When, okay, we have already discussed during the definition of focus. So we had discussed that focus is the point on the principal axis where the parallel rays after reflection meet. Okay, so parallel ray always after reflection goes through the or pass through the focus. Okay, pass through the focus. In this case also, you see this is a parallel ray which is passing after reflection. It is passing through the focus. Okay, this is called principal focus also. Anyway, what I'm trying to say is that, see, we generally measure, not generally, we measure angle of incidence, angle of incidence, and angle of reflection with respect to the perpendicular or normal. Okay, with respect to the normal, right? I'll just tell you, with respect to the normal. See, how do you get a normal in case of curved surface? See, in case of plane mirror, we know this is the normal, right? And we take the incident ray, this one as incident angle of incidence, this is incident ray, this is reflected ray, this is angle of reflection. Okay, so with respect to normal itself, we have to measure this angle of incidence and angle of reflection. So in case of curved mirror or curved surface, how do you get this normal? Actually, see, as this spherical surfaces, for any curved surface, actually you have to draw a tangent at particular point, and then we have to draw the normal to that tangent. Okay, then you get the normal to that particular point on the surface. If this is very, very irregular, but see, we have anyway, the spherical mirrors are actually part of spherical sphere, sorry, spherical hollow sphere. Okay, so if this is the mirror, if this portion is mirror, then what will be the normal to the mirror? Okay, see, normal will be any line we draw on this. Okay, any line we draw on this from the center of curvature, that will be normal. Actually, see, this will be normal. If you take the tangent, so this is normal. Now see, any ray, suppose ray parallel to principal axis comes, so I have to take this as angle of incidence, and if it is going like this, so this we have to take angle of reflection. Okay, so what I tried to say is that you have to always measure the angle of incidence and angle of refraction or reflection with respect to the normal. So any line, see, this cm actually is normal here. Okay, normal to the mirror. Okay, here also same thing, cm, this line is actually, so any line joining, say, similarly cp is actually normal. cp is also normal. So any line joining the center of curvature to any point on the mirror is actually normal. Okay, that line will be taken as the normal, and we have to measure the angle of incidence or angle of reflection or refraction with respect to, in case of mirror it is reflection, so we have to take with respect to that normal. So in this case, I have taken a parallel ray which is passing through the focus after reflection. Now what is angle of incidence? See, this is angle of incidence which is taken as theta, and angle of reflection, as we know, both will be equal to each other. Okay, so that's why angle of incidence and angle of reflection both are theta. So that has been measured with respect to the normal. Okay, this is the reflected ray, and this is incident ray. Okay, incident ray. All right. So this is what I wanted to know, let you know that how to measure the angle of incidence and angle of reflection. So this part is over. Now we are just going to find out the relation between radius of curvature, that is r, and f. Actually it is r is equal to 2f. This is what we are going to. 2f means twice of the focal length is equal to the radius of curvature. That we are going to establish, okay, or derive from this particular figure. I'm just taking for instance, actually both are the same. You can just take any one of this figure, concave or convex mirror. So look, in this case, you know, this point M, see there is a parallel ray which is getting reflected from this particular point M on this spherical mirror, concave mirror, and we drop a perpendicular on the principal axis CP from this point M. And in case of small aperture approximation, this D and P will be at the same point. Okay, I can write MD as a MP for small aperture approximation. I think aperture, not a aperture, small aperture approximation. Okay. Excuse me. So see, if I take this angle theta, then see the alternate angle, I'm sorry, this opposite angle you can say. So this is the theta. So by geometry we can say these are theta. Now if this is theta, if this angle of incidence is theta, so angle of reflection also will be theta. Now just see this figure here. If this angle, total angle is theta, you know, by same geometric consideration we can say this MFD is 2 theta. All right, let me just write in terms of, okay, see so if see MCF, let me write MC P or F, whatever it is. Okay, let me write it as MCP. MCP is theta. MC P or D, same thing actually. This can be written as MCD also. MCD. As I said, this D and P will be coinciding if the aperture of the mirror is small. Mainly, I just wanted to say this angle is theta. So if this is theta, then this is theta. Obviously, angle of reflection also will be theta. So if this angle, this total angle is 2 theta. Look, this total angle is 2 theta, right? So we can write here angle MFD, angle MFD D is also 2 theta. Okay, this 2 I can write, isn't it? Now look, I'll write what is tan theta. see from this particular triangle MCD, from MCD I can write tan theta means perpendicular by base, right? If this is theta, so base will be CD, perpendicular will be MD by CD, right? MD by CD. I'm just taking from triangle MCD, triangle MCD. Now what about tan 2 theta? Tan 2 theta? Tan 2 theta could be written as MD by FD, right? MD by FD. So this is from triangle MFD, from this triangle. Okay, so I have got these relationships, not relationships, in fact we have got these two things. So two things, will keep them. And actually I need some space. What I'll do, I'll just make some space over here. So MD, this particular point we have already understood. See, I'll just get this space. For small approximation, or I'll write this. Okay, let me just erase this part. I hope you have understood this thing. I need this space actually. Okay, now look for, okay, small angle approximation. Okay, okay, performing small angle approximation. That means when the angle theta is very small, theta is very small, so tan theta could be written as theta alone. Okay, so can I write then theta is equal to MD by CD? This I can write, and 2 theta could be written as MD by FD, right? All right, so now I can just take the ratio, or I can just put the value of theta from here to here. See this, I just put the value of theta here. So 2 into MD by CD, and MD by FD is 2 theta, that we had already got. Okay, so from here I can actually strike this MD out, and I can write CD is equal to CD is equal to 2FD. See, CD is equal to 2FD from here. 2FD. Okay. So CD is equal to 2FD. Let me write it here. CD is equal to 2FD. And as I said, for small aperture, for small aperture approximation, what we'll get? We'll get D equivalent to P actually. Okay, dp are same almost, so I can write, see this thing as cp is equal to 2fp. I can write this, cp is equal to 2fp. All right, so cp is equal to 2fp. Now what is cp? Cp is nothing but r, okay, and 2fp, see fp means this thing, okay, this is small f only, so 2f. So this is how we can actually establish the relationship between the radius of curvature and focal length. So what we got, focal length, twice of the focal length is actually radius of curvature, okay. So this particular length will be equal to f then, okay, equal to f. So if we keep one object on the center of curvature, then we should say that the object is placed at 2f distance, okay, 2f distance away. All right, so this is how we can prove this relationship, r is equal to 2f. Now we'll learn about mirror equation. Before that, we need to learn what is called image, okay, and there are two types of image, as you know. So what is called image? See, if you look at here, so these rays are coming from very far object, okay, from very far object. So after reflection, if these rays are meeting at a particular point, then it is called image of that particular object from which these rays are coming. So what is an image? Image is actually a direct one-to-one correspondence between the object and the point where the rays after reflection meets, okay. So rays emanating from a point actually meet at another point after reflection or refraction, or maybe in both cases. That point is called the image of this first point. If I say, see, if I say I have an object, suppose that this is C, this is F. So in between somewhere here, so some ray, if I take parallel ray, you know that will go through the focus, okay. Another ray, if I take through the focus and heat it here, it will go actually parallel like this. And these two rays, when they meet somewhere, these two reflected rays meet together, then they will meet somewhere here. Maybe we'll just see this, okay. This is just a rough sketch. So this particular point, this point is actually called the image point of this particular object point, okay. So I just wanted to say what this line says: if rays emanating from a point actually meet at another point after reflection or refraction, or maybe from both, then that particular point is actually called the image of the first point, okay, where the reflected or refracted rays are meeting. There are two types of images. See, there are two types of images. So one is real image, another one is virtual image. In case of real image, the rays after reflection or refraction really meet, okay. Rays really meet, In case of concave mirror, as you see, we have seen, see this thing, we have seen this, the rays are really after reflection, they are meeting at a particular point. So this point will be called actually real image. Real image. Okay, this point is really real image. So where the rays after reflection or refraction really meet, and the virtual image is that point or that image where the reflected rays really do not meet, but they appear to meet or appear to diverge from that particular point if they are produced in the backward direction. Okay, we'll just see, we'll see these definitions in detail when we see the image formation part. Now let us see, there are few rules to draw images for or images from spherical mirror, or we can say rules for image formation by spherical mirrors. So whether it is concave or convex doesn't matter. When a ray passing through the center of curvature, that will be actually retraced. That means, see, in case of parallel mirror, when in case of plane mirror, when the ray is coming through the normal, it is actually going back like that. Okay, so this is retracing. This is called retracing. So see this Cn. Okay, Cn, it is actually normal to the mirror, Cn. That's why any ray passing through the center of curvature and hitting the mirror will retrace the path. Okay, as you see here. This is one important rule, image formation. Now any parallel ray after reflection pass through the focus in case of concave mirror, and in case of convex mirror, after reflection rays will be diverging in such a way that as if they appear to come from or diverge from the point on the principal axis, which is called focus. Okay, look it here. See the parallel rays are just getting reflected, and upon reflecting they are diverging in such a way that they are just reflected rays are diverging in such a way that they are, if they are produced in the backward direction, then they will meet at focus. Okay, they will meet at focus. Okay, so this is second rule. At any oblique angle, see, if at any oblique angle the ray is reflected, then see angle of incidence and angle of reflection has to be properly determined, drawing the normal, like normal in this case Cm, and for this particular ray, this Cp is actually perpendicular, so this is angle of incidence. So these will be for any oblique ray. When any oblique ray is reflected from the mirror, surface of the mirror, then the law of reflection has to be followed. That means I should be equal to R. Okay, this is for any oblique ray. So I have taken two. One is the parallel ray, which is after reflection passing through the focus, and another ray is the ray which is passing through the center of curvature, must retrace the path after the refraction. So this is how the rules are. Now see, we'll see some image formations by concave mirror. So while drawing the image formed by mirror, we should use pencil and eraser, etc., and a very accurate scale, so that we can just approximately make the distances equal, okay, on either side of the mirror, or any distance reasonably we can take it, right? So suppose there is an object in the figure A. There is an object which is at very far. You look this, these are actually, so these are the rays, these are parallel rays obviously, but this, see, there are dots, right? That means the object is actually seen here now, AB, but it is actually at infinity, which is not seen by naked eyes. Okay, so infinity in general it should be within infinity itself, but mathematically we are just taking this particular object AB now at infinity. That means very far away from the center of curvature. Okay, now we'll be recalling our, or we'll be using our concept we have learned in the image formation part. So in case of this, you know, for image formation, what you have to do, you have to choose those representative rays. One is parallel ray, another one is passing through the center, and maybe you can take any oblique ray. So these two rays will serve your purpose in the formation of images. Let us take these. Okay, so one is parallel ray, which is actually after reflection will pass through the focus. Another ray is actually passing through the center of curvature. After reflection, that will retrace the path. So this is the ray. See, these two are actually meeting at the focus. These two are meeting at focus. So in case of an object which is placed at infinity or very far distance beyond the sea, so see, this is also another ray, parallel ray on the either side of this principal axis or down the principal axis. So this is also after reflection meeting at F. So parallel ray after reflection will meet at focus. So this particular point F, see this particular point, the image will be formed at this particular point, and see the object may be extended, but here we get very diminished image. Okay, very diminished image. We'll discuss the nature of the images. See, so if the object is at infinity, then the image position will be at focus, and it will be highly diminished image. And what is the nature of the image? This is actually real and inverted image. Okay, real and inverted image. So that is what we'll see here. Now let us come little closer. Okay, so I think it should be taken this C figure C. In this case, so we can take the object at 2C, sorry, C, or so the object is at C now. So this distance is equal to 2F. Okay, so any object if we keep at 2F, let us take two rays. One is parallel ray, which is meeting at the focus after reflection. Another ray, okay, another ray we can just take through the center. See, this ray will actually hit here and come back. So this is another ray which we can take. Or we can take any oblique ray. This is, see, if this ray is another oblique ray. So this ray after reflection, since I'm sorry, this is actually the ray which is passing through the focus. After reflection, that will be parallel to the principal axis. I hope that I told you. So any ray which is passing through the focus and hitting the mirror after reflection, that will be parallel to the principal axis. So these two rays will give you the image. Okay, see, these two rays after reflection, they are meeting at this particular point A prime. So you get the B prime and A prime in the, see the image, and you look here, the size of the image will be exactly equal to the size of the object. So A, B will give you B prime, A prime image. Okay, and it is inverted image, and where it is situated at the same place. See, at, so this is object is placed at C. Okay, see, image is also formed, image formed at C itself. Okay, the nature of the image is virtual, same size, inverted, sorry, not virtual, this is actually real, inverted, and having same size. Okay, so I hope you remember this at C. So the image will form between C and F. I'm sorry, this is beyond C. It is beyond C. Okay, so I'm showing you this case. The image will be formed at C itself. Okay, same size but real and inverted image. But if it would have been placed beyond C, then image will form between F and C, and it will be diminished, real and inverted image. So you can see one more case. Okay, this is beyond C actually. This is beyond C. This is beyond C. This is beyond C. This question is beyond C. Beyond C. So the image is formed between C and F. Okay, image is formed between C and F. This is at C. Object is placed at C. Now see, if we keep the object at F, so sorry, between C and F. If the object is kept between C and F, then see the image will be formed beyond C. Beyond C. This is the image. This is now actually enlarged image. Okay, enlarged image. So as you are going towards the pole, okay, as you are going towards the pole, the image is actually is getting magnified. You look at very far distance or at infinity, the image will be point image. So as you come closer to the C point or beyond C, then see this has got some size. At least it is not a point image. Now when we keep at C, that becomes same size. Image become same size as that of the object. Now when you keep the, or you bring the object little further closer, that means between C and F, then the image is still real and inverted, but see it is getting magnified image. Okay, further if we just bring it to the focus, then the image will form at infinity and it will be very large, inverted and real image. Okay, but only one position, see, only one position when we keep the object between P and F, the object, sorry, the image will be behind the mirror. Behind the mirror. the image will be formed at behind the mirror, and so what I'm trying to say is that, I'm sorry, just a minute. Excuse me. So if we keep the object between pole and focus, then the image will form behind the mirror. It will be enlarged, but this will be now virtual and erect image. I'll show you here. See the F, see this F, figure F. See this is F focus and this is pole. So I have kept the object between pole and focus. So I'll take a parallel ray, okay, parallel ray or any ray which is passing through the center. So that will actually retrace. I have to retrace this side like this. Any oblique ray I have to take like this, so that it will reflect like this. So these two ray, see this one and this one, they are no way they can meet. they are actually diverging, or they are going random direction. They cannot meet each other. The MC and PN, these two rays. So if we retrace them, they will meet at this particular point A prime. So we can see, we get, so this is the AB, the image, so this is the object, and the image is A prime B prime. See now, A prime B prime, size of A prime B prime is actually greater than AB, right? This is actually enlarged image, and see the image and object are in the same, like this is the erect image, okay? This is called erect image. Okay, all others say inverted. This is inverted, this is inverted, sorry, yes, this is the image, this is inverted, this is also inverted. Here at infinity a large image will form, that also will be inverted. Okay, but so this is actually erect. So erect image means this is virtual image. Okay, whenever there is an erect image, that is actually virtual. Okay, so in plane mirror we see in plane mirror, if I just keep this, there will be actually lateral inversion, but it will be erect image. Okay, so in case of plane mirror, the image is formed behind the mirror. Okay, image is formed behind the mirror at equal distance. So this we know already, at equal distance, and obviously the image will be erect. So this is actually virtual image. The image we see in plane mirror is actually a virtual image. Okay, actually a virtual image, because the erect image will be always virtual. All right. All right, so this is about image formation by concave mirror. So this is very useful table to understand, at least. So you will not be given this kind of problem at this stage, because you have already learned in class 10 or 9 this particular concept. But the thing is that when we learn ray optics, when we are going to solve numerical problems in like in this standard, so this concept should be clear. Okay, so in case of convex mirror, always the mirror, see, in case of convex mirror, image will be always virtual. See, if I keep this at infinity, then a point image will be formed at this point, where at the focus behind the mirror. See, the image is formed behind the mirror. See, this image distance is denoted by, say, PF here. The image distance is actually denoted by u, sorry, v, and object distance is denoted by u, which is here infinity. All right, so image is actually formed behind the mirror. So this is a virtual image. It will be erect but diminished image. So if you just bring it closer to the mirror or pole, then also see a very diminished image and virtual image will be produced. So mirror the image will be produced behind the mirror. It will be erect. It will be diminished in size. Okay, so these are the things. Okay, so if you keep just between pole and focus, any point, okay, between infinity and pole, anywhere you keep, the image will be formed between P and F. So in between this, okay, in between P and F, the image will be formed. It is true for any place you bring or you keep the object in case of convex mirror. So one good thing I'll tell you here, if you bring, as you bring the bring the object nearer to the near to the pole, the image will be coming closer to the mirror. See, this will be always found between pole and focus, so it will be actually just position will be shifting towards pole, okay, or towards the mirror, and it will be highly diminished image. Diminished image. It will be very diminished, very small images as you come closer. See that means, you know, if you bring the object near and near here, the image will be coming towards this way, this way, this way, and you know that will be very smaller and smaller size of image will be formed, okay, in between this pole and focus, okay. But always, I'm sorry, always this and always the image will be a virtual one and erect one, okay. I think I'll stop it here for today. Tomorrow if we start, okay, I think we'll do it tomorrow. Mirror equation, linear magnification, then image formation. Okay, image formation we have already seen this part. Mirror equation part will take little time to like derive the formula, but I'll just tell you the mirror equation and then tomorrow we'll discuss the rest of the thing. See, the distance between the object and the pole, that is called object distance. Object distance. This is called object distance, and object distance is always denoted by u, small u. And see, the distance between the image and the pole that is called image distance. Okay, so in this case actually object distance is, see, in this case BP. In fact, we should write PB because we will be measuring the distance from the pole or from the origin. So this PB, image distance. So image distance is denoted by always small v, and it is in this case, this is PB prime. This is measured from pole towards the left. So in this case, as I said, this will be negative. This will be negative in size. When we do the numerical problem, I'll tell you how to take the signs of the distances. See, focal length, focal length, focal length f. It is denoted by f, and in this case, what is this? So it is actually PF. PF. This is the focal length. Okay, and this is also negative in this case. Negative since it is measured in the leftwards. Okay, in the negative x-axis direction. So mirror equation will see that it is 1 by u plus 1 by v, that will be is equal to 1 by f. So this is actually mirror equation, which we will be developing or deriving this equation in the next class. Okay, so this we have to derive and see how it comes. All right, so thank you for your patience. Bye for today.